Okay, lads and ladies, welcome back to MAC 1140, section 009. Looks like folks are still trickling in. I'm not sure. Make sure the link's up in the right place. It's been there for a minute. Yeah. All right. Well, we got a small group today. That's okay. Let me turn on the screen share and we can start talking about the good stuff. Today, we're going to continue kind of where we left off last time. So last time we worked our way through the section on transformations, right? How to transform one function's graph into another function's graph. And there were 4 basic rules. Today, we're going to look a little bit more closely at 2 of those basic rules and how they fall into a classification scheme that mathematicians really love. To that end, we should go ahead and begin because it is time. This is MAC 1140. Section 009, which is a pre-calc class, and today is the 14th of September, 2021. Today, we're going to finish section 2.6 on transformations. And that links up very nicely with the next section, 2.7 on combining functions. So just a little word at the start here. A lot of people assume that what mathematicians do is like solve big arithmetic problems or big algebra problems or even big calculus problems, that we're working to like find some number, right? Like all the time. This is just some big calculation that eventually, someone with the right skills will be able to grind out. That's not true. So what mathematicians do with their time is try to prove theorems. Theorems are just true statements, and they're consequences of the basis for reasoning, which are called axioms. So every mathematician has some set of axioms with which they operate, the basis of reasoning, things they assume to be true. And then the work of a mathematician is to prove consequences of those axioms, and they can get pretty complicated. One of the big tools that people use to that end is to study different spaces. So a space to a number theorist or a mathematician in general is a very general term. It's just like, a set with some structure. The most common sort of spaces that you deal with are like the real numbers. The real numbers form is called a vector space. There's lots of other names you could give the thing, but it's a space. And the objects in there are numbers. And when we study the real numbers, we look at functions whose inputs and outputs are real numbers, right? The variables represent numbers. Kind of what we're going to talk about today, and more so what we're going to talk about as we go in deeper into section 2.7, is starting to study spaces of functions, where the variables, rather than representing numbers, represent a whole function, and then studying relationships between those functions. Turns out that is a big part of what mathematicians do. And one of the ways you can do that, one of the ways you can facilitate the study of a space of functions is by coming up with categories into which you can kind of sort the functions. And then you can start trying to say, every function of this type has this property. Very useful. One of the most important set of categories like that are even and odd functions, kind of like even and odd numbers. So let's get to it. We have to begin with a definition here today. So the function f is called an even function if, I'm going to give you two different ways to think about this. The first is an algebraic definition, and that is f of negative x equals f of x. But then there's also a really important way to interpret this geometrically. And the reason it shows up in the transformation section is because this is a transformed version of the function f. So I'll remind you, I guess we should probably go through a quick reminder. But when you multiply on the inside by a number, that's a horizontal scaling. It's a special kind of horizontal scaling. This is what's called a horizontal reflection. So multiplying on the inside by a negative number here, like multiplying on the inside by a -1, we saw how multiplying on the inside by a 3 will squish you down horizontally, or how multiplying on the inside by 1/2 will stretch you out horizontally. If you multiply on the inside by a negative number, in addition to doing whatever squeezing or stretching, just -1 on its own flips you over the y-axis. That's what this transformation does. So another way of seeing this is that the graph of f is invariant and doesn't change under the transformation reflect over the y-axis, which I'll usually just refer to as a horizontal reflection. All right, so I think we saw just 1 or 2 little examples of reflections on Tuesday, and I want to look a little more carefully at them today. But this thing right here is a special case of a transformation, right? This is f of some constant times x. And we learned on Tuesday that that's a horizontal scaling. The special scaling, where you're scaling by a factor of -1, that's going to multiply all your x values by -1. And what that does is it flips all the points over the y-axis. So this is the definition of an even function. There's a similar one, the function f is called an odd function if f of -x is equal to -f of x. And to interpret this in terms of transformations is a little bit tougher, but we can think about what each of these things does. This guy, same as this guy. That's a horizontal reflection. So to get the graph of f of -x from the graph of f, you would flip over the y-axis. This guy over here, -f of x, the negative on the outside, that's a vertical scaling, right? This is like 2 times f of x or 5 times f of x, only instead of a 2 or a 5, it's a -1. So that's going to multiply all the y values on your graph by -1. And what that does is flip you over vertically, flips you over the x-axis. So this means the graph of f looks the same if you flip horizontally as if you flip vertically. All right. So these are just special cases of the transformations, right? Let me insert here a little recall. F of c times x, this is a horizontal scaling. And if c is -1, remember the way this works. To get the graph of f of cx, you multiply on the inside by a constant, you would divide all the x values by c, right? You take the original graph, the graph of the parent function, divide all the x values by c. That'll shrink you in if c is bigger than 1, and it'll stretch you out if c is between 0 and 1, smaller than 1. The special case here where c is -1, this is a reflection over the y-axis, which again is a horizontal reflection. Also, a constant times f of x, like multiplying on the outside by a constant. This is a vertical scaling. And the special case here, if c is -1, this is a reflection over the x-axis, or a vertical reflection. All right, so these are the two special cases of the scaling rules that we met before. We looked at some horizontal scalings and we looked at some vertical scalings, but I don't think we had a lot of opportunities to look at these special cases, the reflections, maybe one. So the first thing I want to do today is just get a little bit of practice performing these transformations, doing some of those together. And then we're going to try to understand this even and odd business in terms of those transformations. One more thing to tell you, even and odd, those are words that we're familiar with from whole numbers, right? Whole numbers are either even or odd, they're divisible by 2 or not. That's called parity, P-A-R-I-T-Y. So when you hear me say the word function parity, that means even or oddness, right? It's just that even or oddness is a weird turn of speech. So it's easier to say the word parity. Okay, so first, a little bit of practice, just implementing these reflections, and then we will try to understand them through the lens of function parity. Oh. So some examples, right? We're just going to sketch some graphs. Don't worry about even or odd. We're just going to sketch the graphs. Let's sketch f of -x and negative f of x for the functions first, let's look at f of x equals x to the 4. Give ourselves some space. And we can look at f of x equals the square root of x. Let's do that one. And then we'll do one more. How about f of x equals 1 over x? All right, so we're going to start up here. So I'm starting with the graph x to the 4. That's my parent function. And I'm going to use that to sketch f of -x and negative f of x. So first, is y equals f of x, the original, x to the 4. We know he has that same basic shape as x squared, but he sticks to the bottom a little bit harder. It looks a lot like x squared. It's just kind of a little bit flat down here. Some points that we know are on this graph, 0, 0, the origin. 1, 1, and -1, 1. And 3 points we know for sure are on the graph of that parent function. You could, if you forget that, you could always just plug in a few numbers, but hopefully this is clear in your head at this point. The two functions I want to graph from this are f of -x, which is the horizontally reflected version, and negative f of x, the vertically reflected version. So over here, let's sketch f of -x. I'm going to pick this up and flip it over, right? So this point right here, 1, 1, he's going to get sent to -1, 1. All right, I'm flipping him over, or if you like, dividing all the x values by -1. Same rule that we met before, just a special case. 0, 0 is going to stay 0, 0. And this point, -1, 1, when I flip everything over, is going to come over and sit right here at 1, 1. So overall, here's that new graph. And you notice this is the same as the original graph, right? Here's the original, f of x. Here's the transformed, f of -x. This graph is identical to the graph we started with. That's what it means to say that this is an even function, right? It's invariant. The graph doesn't change when you flip it over horizontally, when you flip it over the y-axis. And then lastly, we want to look at negative f of x. Well, that means I'm going to take this original graph and I'm going to flip it over the x-axis. I'm going to flip it over vertically. So this point is going to come down here. This point is going to come down here. 0, 0, the origin stays there. And it's not just those points. Every point on this branch is going to get flipped down here. Every point on this branch is going to get flipped down here. So the result looks like this. That's the vertical reflection. Any question about where any of these graphs are coming from? And again, if you're looking for a rule that you can use that always works, to get c times f of x, you multiply all the y values on the original graph by c. So here to get negative f of x, I'm just multiplying all the y values by -1, keeping the x values the same. To get f of cx, you would divide all the x values by c. So here, to get this guy, I'm dividing all the x values here by -1. So this guy, -1, +1, 1. When I divide that x value by -1, he becomes -1, 1. And we do the same thing for every point on the graph. And again, the fact that these two are the same is what it means to say this is an even function. Okay. Let's do the square root. The original function or parent function here. We know what this looks like. It's that upper half of the sideways parabola, right? There's the origin, got 1, 1, because the square root of 1 is 1. And if we go out far enough here, we get to 4, 2. This is y equals f of x, the origin. To graph y equals f of -x, I would reflect this graph horizontally, meaning I'm going to take every point and flip it over the y-axis. So this would be y equals f of -x. And same rules, right? I'm just going to take all the x values and divide them by -1. So 1, 1 is going to go to -1, 1. 4, 2 is going to go to -4, 2. And 0, 0 is going to stay 0, 0. So there's what we would get by doing that horizontal reflection. And just picking up the graph and flipping it over like this. And then the vertical reflection, if I just wanted to do that, a little short on space here. If I take this original graph and I flip it over vertically to get -f of x, that means I'm taking all the y values on this original graph and multiplying them by -1. So 0, 0 is going to stay 0, 0. And the whole picture just flips over the x-axis. So he will look something like this. We now have 1, -1. And somewhere out here we'll have 4, -2. This function, if you look at the original and the horizontally reflected version, this graph is not the same as this graph, right? This graph doesn't have anything in quadrant 2. This graph has everything in quadrant 2. This graph doesn't have anything in quadrant 1. This graph has everything in quadrant 1. So these are definitely not the same. So this guy, definitely not an even function. The last fella here is probably the most interesting. 1 over x, one of our parent functions. I know what this looks like. It's got the point 1, 1 right here. The point 2, 1/2 right here. And there's a matching piece on this side. One of the points over there is -1, -1. So this is the graph y equals f of x. This is the original. If I flip him over horizontally, let's see what we get. So this point 1, 1 would get flipped over here to -1, 1. This point 2, 1/2 would get flipped over here to -2, 1/2. And this whole piece here would get flipped over into this whole piece right here. And the same thing's going to happen down here. If I flip this whole thing over, right, if I flip this all over, this whole branch is going to get flipped over to here. In particular, the point -1, -1 is going to get flipped to 1, -1. And this is the graph y equals f of -x, right? We did the horizontal reflection. Now watch what happens if I did the vertical reflection instead. I'm going to come back here to my original graph, and instead of flipping it over horizontally, I'm going to flip it over vertically. That's how we get the graph of -f of x. All right, I'm going to start with this branch. I'm going to flip this over vertically. And so multiplying all the y values by -1. So 1, 1 goes to 1, -1. 2, 1/2 is going to go to 2, -1/2. So this branch gets flipped vertically down here. This branch is going to get flipped vertically up here. Interesting. In particular, the point -1, gets flipped to -1, +1. What do you notice about the two graphs on the right? Show me you're engaging. What do you notice about these two graphs?
They both have the point -1, 1, and 1 and -1.
Are there any other points that you think might be common to these two graphs? Yeah, it's there in the chat. Not just those points. It's true that -1, 1 is common to both. That 1, -1 is common to both. This point, 2, -1/2 is common to both. He's just unlabeled. He's right here on this guy. This point, -2, +1/2 is present over here. He's just unlabeled. He's right here. They're the exact same graph. They're literally the same graph. So just like in part A, where the horizontal reflection gave us the same as the original, here, the horizontal and vertical reflections being the same, means f is odd. F of -x is the same as -f of x. These sort of invariant properties are exactly what mathematicians love. It's precisely the type of thing you want to use to sort mathematical objects into different boxes. They're called equivalence classes. So what we've discovered is that 1/x is an odd function, in addition to getting practice with these. And x to the 4 is an even function. Okay, any questions on any of these graphs? Your current homework has more similar stuff to the previous one, in that there's more graphing of transformations. This time, the problems are focused on the reflections. I've tried to slim it down as much as I can for you. But in addition to this more graphing of transformations, there are questions about even and oddness, which you can answer graphically like this. I'll give you other ways to think of it too, but I just wanted to highlight that. One other thing while I'm talking about the homework, as you work those homework problems, you must draw the graphs by hand. If you get into the habit of just like clicking around so you get the right one, it's going to destroy you on the test. You must practice drawing these graphs by hand. It's the only way to get good at this stuff. As long as you do that, the test, I promise, will go well. And also, I promise you there will be problems on the test that ask you specifically to do this sort of thing. Okay. So if I want to know whether a function is even or odd, I can graph the original function, graph the horizontally reflected version, and graph the vertically reflected version and see if anything matches up. This guy, the square root of x, he's neither even nor odd because these two aren't the same. That's what it would mean for them to be, for this to be even. And these two aren't the same. That's what it would mean for this to be odd. In writing, I'm saying this, just call it a fact. Functions can be even, odd, or neither. Another fact is if a function, actually let me hold off on this second one. and instead give you a question. So if I have the graph, I can try to tell you whether the function is even or odd. How can we tell if a function is even or odd without the graph? Or is there a faster way? To recognize parity than graphing all three functions, the original, the horizontal reflection, and the vertical reflection. Yeah. So Suzanne in the chat has discovered something, that if you're looking at a simple power function and the power is an even integer, then that's going to be an even function. And if you're looking at a simple power function and the power is an odd integer, then that will be an odd function. Unfortunately, it's a little more complicated than that. Like cube root, a cube root of x is also an odd function, but 1/3 is not an odd number. So we can investigate both of these questions a little bit more clearly. Let me look at the second one. So rather than graphing all three of these things, if you just have the graph of f, you can tell if your function is even or odd. Even, odd, or neither. So the graph of an even function when we say that this function is invariant under the horizontal flip, there's another way of interpreting that. In order for a graph to be invariant under that horizontal flip, it has to be symmetric about the y-axis, right? If it's going to be the case that when I pick you up and flip you over like that, you stay the same, that means whatever is here has to perfectly mirror whatever is here. So the graph of an even function will be symmetric about the y-axis. And you can see precisely why that's the case. I'll take my favorite x value here, I'll just call it x. Look at the point on the graph associated with that. That's x comma f of x. And then I'll take the symmetric point over here, which is negative x, and look at the point on the graph. This is the ordered pair negative x comma f of negative x. And you notice that those y values are the same. Well, what are the y values? It's f of negative x over here and f of x over here. They're at the same height. So the y values are the same. And what are those y values? Well, one of them is f of negative x, the other one is f of x, i.e. f is even. So, maybe this is 3. And this is the point 3 comma f of 3. And this is -3. So this would be the point -3 comma f of -3. You see that f of -3, the y value here, is the same as f of +3, the y value here. And as long as that's true for every x in the domain, not just for 3, but everywhere, that forces these heights to always match, which forces this symmetry about the y-axis, right? So we're symmetric about this vertical axis. If you were to fold this up, they'd sit right on top of each other. And there's a similar thing for odd functions. Do my best to draw a sort of generic odd function here. The type of symmetry here is slightly more complicated. Space in here. The graph of an odd function will be symmetric, not about the y-axis or about the x-axis, but about the origin, about the point 0, 0. And we can see how that connects to the definition. Again, take your favorite x value. Maybe this time I'll take them over here. Look at the point on the graph associated with that x value. If you reflect that point straight through the origin, you will get another point on the graph. And that other point will necessarily be at the opposite x value, the negative of that. So this is the ordered pair x comma f of x. This is the ordered pair -x comma f of -x. This is the point on the graph of -x. And what you see is that the height, look at just the y value. Here's the negative, here's f of -x. And up here is f of x. They're not the same, right? They're not at the same height. Those y values are different. But this y value is the same size as this y value. It's just that this one is in the other direction. He's negative, he's positive. So here, the y values, f of x and f of -x, are the same size. But opposite sign. And that is literally the same thing as saying f of -x is the same as negative f of x. Same size, opposite sign. All right. So again, if you have the graph, it's fairly easy to tell if your function is even, odd, or neither. You're going to look for these symmetries. If the graph exhibits origin symmetry, then you're looking at an odd function. If your graph exhibits y-axis symmetry, then you're looking at the graph of an even function. This is not terribly hard to do. Let's do it a few times quickly. So just using the graphs classifies even, odd, or neither. What haven't we looked at yet? All right, this should go nice and quick. The graph in part A, is that the graph of an even function, an odd function, or neither?
It's even.
Good, yeah, this is an even function, right? If I take this piece and fold it over here, it sits right on top, have y-axis symmetry. Okay, what about the graph in part B?
Odd.
Yeah, this has origin symmetry. Means this has to be an odd function. And the last guy?
It's neither.
Good, this one has neither symmetry. This one is neither even nor odd. And you can always check this a little bit more carefully, right? Just take your favorite X value and check. Does this reflect over to a symmetric point here? Yeah, this guy has that y-axis symmetry. Or if you take your favorite generic point here and reflect through the origin, do I land back over here? Yes, I do. So, okay, he has origin symmetry. This fella, no dice, right? If I take an X value like right here, and I try to reflect it across the y-axis, I get nothing. And if I try to reflect it through the origin, I get nothing. So he is neither even nor odd. But what if you don't have the graph? What if the function is not just a power function? What if it's not one of your parent functions and you don't know what the graph looks like? Is there any way to detect even and oddness without making use of these symmetry arguments? Maybe more importantly, is there any way we can use even or oddness to help us graph functions? Like if you knew that this was an even function and you had this piece of the graph, you could immediately draw this piece of the graph just by reflecting it. Or if you knew that this was an odd function and I gave you this part of the graph, you could easily draw the rest of the graph and have the whole picture using the origin symmetry. So wouldn't it be nice if there was a way for us to tell if a function is even or odd without already having the graph? Because if the answer to that is yes, this is even, or yes, this is odd, that can help you draw the graph more quickly.
We can check the power if it's even power.
That will work sometimes. So if your function is a power function and that power happens to be a whole number, then that rule works. But there are plenty of functions that are even or odd, but are not straight up power functions. Like this guy right here. Oh, this one is a power function, but the exponent here, this is like x to the 1/3, right? And 1/3 is not even or odd. And then there are other functions that do exhibit even or oddness, but are not even power functions. They're more complicated. So
if we can divide the whole power, the whole function by 2, it's gonna be even, and if you can, it's gonna be odd.
something like that. So remember, it's possible to be neither even nor odd. So once we've ruled out even, we can't conclude odd. But let's look at this. Let's see if we can detect function parity using algebra. The big idea is this. We write down f of negative x. If that simplifies to f of x, then f of negative x is equal to f of x, so f is even. If f of negative x simplifies to negative f of x, then f is odd. And if f of negative x simplifies to neither, neither the original nor its negative, then f is neither even nor odd. That's all. So we use the definition, right? We use the definition and our algebra manipulation skills. The bad news is that, like I said before, just looking at the powers isn't quite enough. There are some functions that have a mix of even and odd powers and turn out to be even. There are some functions that have a mix of even and odd powers and turn out to be odd. And there are some functions that have powers of x which aren't integers, right? Are not whole numbers. So we can't even talk about the power being even or odd. But there are special cases where rules like that work, specifically for polynomials. But let's take a stab at this. Just going to use the definition. Determine algebraically if the function is even, odd, or neither. And we'll do this for a few guys. We can look at x to the 5th plus 2x. I'll leave some space there. We can look at g of x equals 1 minus x to the 4. We can look at h of x equals x over 1 plus x squared. And we can look at, I'll call it e of x equals, what should we do here? Something more interesting. Yeah, how about, all right. So each of these are a little bit complicated to graph, right? Like I genuinely don't know what the graph of this looks like. We could get this one as a transformation. This one, unless you remember how to graph rational functions from your pre-calc class, no dice. This one, it's a quadratic. You probably remember how to graph that, but graphing these would take time. Graphing these would take time. And our graphs, my drawings are not always perfect. So maybe it would be possible to make a mistake. But if we look at f of negative x, I know what that is. Remember your first homework where you had to evaluate like f of 1 over x, f of negative a, all that shit, right? That's where this function notation is going to come back in handy. You just take this definition for f, and everywhere there's an x, you write negative x in parentheses. And holy shit, do these parentheses matter? Do not skip them. Yeah, sure. So sorry, we're gonna come down here just a little bit. Yeah, there we go. So we're gonna start by writing down f of negative x, and then we check to see if that simplifies to the original f of x. If it does, then f is even. On the other hand, if f of negative x simplifies to negative f of x, then f is odd. And if neither of those things happen, then the function's neither. So here my goal is to simplify this. And the obvious challenge is this negative x to the fifth, right? How do I deal with that? There's more than one way. Let me show you a simple way. Maybe not the simplest, but it'll give you a hint as to how the rule usually works. If you take negative x and raise that to the fifth power, that's negative x times negative x times negative x times negative x times negative x, right? 5 times, 1, 2, 3, 4, 5, all multiplied. These first two guys, if I multiply negative x by negative x, that's a negative times a negative, so it's going to be positive, and x times x is x squared. So first duo multiplies to x squared. Same with this next duo, negative x times negative x there, that's also going to be positive x squared. And then I've got one copy of negative x over here. X squared times x squared, that's x to the 4. Remember those basic rules for exponents. And then we're multiplying that by negative x. Positive x to the 4 times negative x to the 1 is negative x to the 5 with no parentheses. And it's worth noting that the general rule is if you take negative x and raise it to an odd power, that's going to be the same as negative x raised to that same odd power, no parentheses. Because you can just do this. You can pair up x's into even powers, which will be positive. But then you're going to have one left over, because that's what it means to be odd. It means you're one greater than a multiple of 2. And the other way here, if you take negative x and you raise it to an even power, then you're going to be able to pair everything up. So in the end, everything will be positive. This is just going to be x raised to that even power. And you can think of it as going like this, right? There's other ways to do it too, but this is most accessible. So negative x to the 5th in parentheses is the same as the negative of x to the 5th without parentheses. And then plus 2 times x, that's the same as minus 2x. And at a glance, this doesn't look like the original function, does it? This looks pretty different from this. So remember, my goal is to see whether f of negative x simplifies to the original, or if f of negative x simplifies to the negative of the original. I don't think there's any hope of simplifying this into the original function. That's not going to happen. But does anybody see an algebra step I could do here to make this look like the negative of this?
We need to put minus and then parentheses.
Yeah, exactly. Which is, and that's the same thing Suzanne just said in the chat. We can factor out a negative. So if I factor out that negative, I'll have negative parentheses x to the 5th plus 2x. And that x to the fifth plus 2x is this original. So that's negative f of x. In other words, this is an odd function because f of negative x simplified to negative f of x. Okay, we're going to do the same thing with the other guys. So are there any questions on what we did here or how any of this stuff worked? Okay. G of negative x. Same deal. This is 1 minus, and then here I just write negative x in parentheses. Swapping x for negative x. And now by this rule, negative x raised to an even power is the same as positive x raised to that same even power. Tells me this is 1 minus, this minus is this minus, regular x to the 4. And that's my original function. So this guy is even. And both of these, you could have applied that rule that people have been mentioning, right? Here, all of the powers of x are odd, and it turned out to be an odd function. Here, all the powers of x are even. This constant, by the way, we think of that as an even power of x. That's x to the 0. If this had a constant term, it would not be odd anymore. He also follows that rule, right? All the powers are even, and he turns out to be an even function. The next fellow has a mixture of odd and even powers of x. Let's see what happens with him. Let me start over here. H of negative x for this guy. Same thing, swap x for negative x in parentheses. So that's negative x over 1 plus parentheses negative x squared, like this. Downstairs here, this negative x squared, that's negative x to an even power. So that negative will go away. Upstairs here, there's no power, or if you like, the power is just 1. So it's just going to be negative x. 1 being odd. So this is negative x with no parens divided by 1 plus x squared. There's one last thing I can do here. If I have negative 3 divided by 10 or whatever, that's the same as having the negative out front, and then 3 divided by 10, or in this case, x divided by 1 plus x squared. So this negative upstairs here, he can come out front. And the thing that's left over when you do that is the original function. Right? This is negative h of x. So h of negative x simplifies to negative h of x. This one is also odd, even though he has a combination of even and odd powers. The rule that I'm employing there, might seem a little silly to say, but just to be clear, having a factor of -1 upstairs is the same as having a factor of -1 out front. In fact, having a factor of anything upstairs is the same as having that factor out front of the fraction. Okay, and now we come to our last guy here, e of x. Let's take a look at him. E of negative x is 2 times negative x minus negative x squared, which is negative 2x minus x squared, following this same rule. Up here. And now I ask myself, is there anything I can do to turn this into the original? Or is there any way I can factor out a negative and get the original left over? We can factor out a negative here. When you do that though, you get 2x plus x squared, not 2x minus x squared. So this is neither e of x nor is negative. So the function e is neither even nor odd. And that's it. That's how you can tell just using algebra whether your function is even, odd, or neither. If you have the graph, you can use that, and that's dope. Graphs are wonderful, but you don't always have the graph. And sometimes knowing whether your function is even or odd can make it easier to graph. If you know the function is even, you know to expect that symmetry that can help you draw your graph. So remember what the rule was, right? And this is just the definition. The definition is of an even function is one where f of negative x is equal to f of x. So if f of negative x simplifies to the original, then that function is even. If f of negative x simplifies to negative f of x, then the function is odd. So it doesn't have to, it's not that it has to be the same function in order to be even or odd. It's if f of negative x simplifies to the original, the same, then f is even. And if f of negative x simplifies to the negative of the original, then f is odd. But in either of those positive cases, you should be able to recognize your original function in there somewhere, either with a negative out front, that means you're odd, or just straight up being the same as the original, that means you're even. Yeah, it's really not too bad. It's not too bad, but you do need to practice this. I promise you, this is another one of those things like graphing. As you do the homework, you got to draw those graphs by hand. Otherwise, you won't have the practice for the test. This is one of those things that you want to practice a little bit, at least before the test. So some of those problems in your homework are going to ask you, is this function even, odd, neither? Try approaching them different ways. Try approaching them by looking at the graph if you know what the graph looks like. Or if you don't know what the graph looks like, try approaching it like this from the algebra perspective. It is a common question on my first test in this class to say, show algebraically that this function is even, odd, or neither. And nudge, wink. All right, let me see how we're doing for time. We'll decide whether to move into the next bit. Oh yeah, a couple quick, simple rules. We haven't defined the term polynomial yet, but if a polynomial contains only even powers of x, then that polynomial is an even function. And similarly, if a polynomial contains only odd powers of x, then that is an odd function. This is something that you guys conjectured in the chat, and you're correct. But the requirement here is that the function be a polynomial, right? Like we saw that last problem set, last example, this guy has both odd powers of x and even powers of x. So he would appear to violate this rule. Oh, but he's not a polynomial, right? There's like variables going on downstairs here. This is not a polynomial. So this being odd doesn't violate this fact. but you do need to make sure you're applying that fact correctly. Another place we should kind of be careful, if you look at g of x here, it's tempting to say this only has even powers of x because it just has this x to the 4, but you got to watch out for this 1. This is an x to the 0, and 0 is an even number. Remember what even means, divisible by 2. 0 is divisible by 2. 0 divided by 2 is another integer, it's 0. So constants count as even powers. So if you're going to use this fact, right, it is a true statement, and you can prove it. It's not terribly hard to prove. If you want to use it, proving it would be a really good idea. Just remember that constants count as even powers, and that it only applies to polynomials. All right. Fun questions for you to think about. If f and g are both even, what can be said about f of x plus g of x? Is it automatically even? Odd? Neither. What about f of x times g of x? Or f of x over g of x? And so on. And you could swap even for odd. All right, so why do we call these things even or odd? It's true that, like, if I multiply 2 even numbers, I get another even number. If I add 2 even numbers, I get another even number. Is it true that if you multiply 2 even functions, you get another even function, or add 2 even functions, you get another even function? Take some time to think about this question. It's a good one. And it also serves as a really nice introduction to the next section. So I'm not going to go on. We're going to end a little bit early today here, it looks like, and that's okay, just a few minutes. But the next section in the textbook, section 2.7, is all about combining functions like these. So this top function here, we could call him f plus g, right? In the same way we call f of x just f, I could give this guy the name f plus g and then study him as his own function. Or I could call this guy f times g, and he's defined to be f of x times g of x. I could call this f over g. So next time we're going to look at these ways of combining functions plus a couple others, specifically the composite function f of g. We will be playing with next time. So let me add him too. And there are other permutations on this type of question. Like you could say, what if f is even and g is odd? Then what can you say about f times g or f over g or f of g? All of those would be fun questions. And they're the types of things that tend to show up on true-false questions in an exam. So I strongly encourage you to try to answer this question. I'm not gonna go through the proof in class for all of these, but next time I'll prove maybe one of them to give you an idea in case you're struggling answering it on your own. But it's not a terribly hard thing to do. You guys are all capable of it, so I invite you to do that. Quick reminder, you have some shit up in WebAssign to be working on. I posted another homework set for you today. It's the second part of 2.6 and the first part of 2.7. It's not anything terrible. There's some more graphing using transformations, but with the emphasis on reflections, because those were almost completely absent from the previous homework set, so we didn't have time to get to them on Tuesday. The other thing, of course, is lots of even and oddness. So lots of questions about function parity. So some of the same sort of stuff we've been seeing, but with more reflections, and then lots and lots of new stuff about even functions, odd functions, and whatnot. So I'm going to give you until next Tuesday to finish this. I'm not rushing this because I wasn't thinking we would get to all the 2.7 stuff in here, and indeed we're not. So this isn't due for you until next Tuesday, but please try to finish up through, where is it? Yeah, try to finish up through question number 24 by Tuesday, all right? If you get done with number 24 and all the stuff before it by Tuesday, you're in good shape.
and then by Thursday, then you're in good shape, and we'll pick up with things like this in class on Thursday with section 2.7. Alrighty, any burning questions for me before I let you guys go? Okay, then I'm gonna go ahead and end the meeting here. Please work hard on that homework. If you're stuck on anything, come see me in office hours, send me a Canvas message, post to Discord, and I will see you guys on Thursday. Remember, Thursday is a big day for us. We're gonna talk about the test. So your first test is getting close. We are not far from it at all. After we finish section 2.8, it will be time for the test. See here. So combining functions, this is where we are now. We have just one section after that before exam one. Exam one is just 1.1 through 2.8. So probably late next week or early the following week. We'll set the exact date in class tomorrow, or on Thursday, sorry. But that's it from me for today. I hope you guys have a good rest of your day. I'll see you next time.